Hello and welcome to this new video. In this video, we are going to start chapter 1 about finite Markov chains. Okay, so there will be 5 sections in this chapter. In this video, I'm going to cover the first part of section 1.1 and I'll continue in the next video, the remaining. Okay, what are Markov chains? So I think that in previous probability courses, you already studied what we call independent or IID, dependent and identically distributed random variables. This is the simplest case of stochastic processes. And you observe that the condition of independence is not always satisfied. So the next complicated processes after independent random variables are the Markov chains. Okay, so they possess a kind of conditional independence, as you shall see. But before I start, let me give you a known example. If you ever played the snake ladder game, Serpent Échelle, if you ever played this game, then you already know what is a Markov chain. Okay, so you start with position 1 and you throw a die, and according to the number obtained, you move a number of steps. So if you start with 1, you can move to state 2 or 3 or 4 or 5 or 27 or 7, right? With equal probabilities. Okay, and suppose that at some point you reach state 43. If you are in state 43, then you can move to state 44, 40, in this example, of course, 46, 19, and 48, and 49, right? So there's a certain number of states that you can visit actually at each step. So, but of course, the system is stochastic, so we cannot predict the future with certainty, but we can compute probabilities of the future. Now, if we know that we are in state 43, in position 43, then predicting the future or computing the probabilities related to the future, in order to do that, the knowledge of the history is irrelevant. So if we want to compute probabilities, it's irrelevant how did you get to state 43. So this is another idea behind Markov chains. The first idea behind Markov chains is that it's just simply an object moving between states with certain probabilities. But if we dig a little bit deeper, we see that there's another idea here. There is the idea that the probability of the future, given the present and the past, is independent on the past. Okay, so the past, of course, influences the future, but only through the present. Okay? This is the idea that you shall take as a definition now. Okay? Now, of course, you may have other configurations of this game. It's not really important, but the idea is the same. So, two ideas now we have. An object moving between states with probabilities, and second idea that given the present or the current situation, the knowledge of the past does not influence or does not affect the probabilities of the future. Okay, so once again, if you are in state 43, let us say in this case, it's not really important how did you get to this 43 state, right? In order to compute or to predict the future. Okay, so now this is the Markov equation, if you like, verbally. The probability of the future given the past and the present is equal to the probability of the future given the present. Okay, so this is the kind of conditional independence, if you like. And if you studied mechanics, actually, you may have encountered a similar idea that if you want to predict the future evolution of a mechanical system, you don't need the full history. You just need the initial position and the velocity. Okay, so the situation is here similar, but in a probabilistic context. Okay, so we cannot predict the future here precisely as we do in mechanics, but we can compute probabilities. The best that we can do is to compute probabilities related to the future. Okay, so let us put this equation into a more precise mathematical way. So if you have a sequence of random variables, so we have a discrete time stochastic process, and each random variable takes values in a finite set that I call S, which is of the form 1 to L or 0, 1 to etc. up to L. It's finite. So we say that Xn is a Markov chain if this equation holds. So how to read this equation? So what I call the past is the event x0 given x1, etc. up to xn minus 1. This is the past. The present is time n, and the future is at time n plus 1. So this is just a translation of the idea that the probability of the future given present and past is equal to the probability of the future given only the present. Okay, and of course, since when we deal with conditional probabilities, we divide by this event, so we have to assume that it's not zero. Okay, so this is the precise mathematical definition of a Markov chain. Now, if you look at this probability, this is what we call a transition probability. It depends on three variables: I, j, and n. Now, it's possible that this probability does not depend on n. If it does not depend on n, we say that the Markov chain is time homogeneous or just homogeneous. Okay, so there are homogeneous Markov chains and non-homogeneous Markov chains. But in this course, we'll focus mainly on homogeneous or time homogeneous Markov chains. If this transition probability is independent on n, we denoted it by Pij. And when I and j vary in the finite set, we obtain a matrix. L times L or L plus 1 times L plus 1, depending on which state you start with. Okay. And this matrix is called the probability transition matrix of the Markov chain, or just the transition matrix of the Markov chain. Okay. And studying the properties of this matrix is one of the objects of this course, of this chapter. Okay. And the state S where Xn takes values is called the state space of the system or of the Markov chain. Okay, so as we said in this chapter, it will be finite, and the next chapter will be infinite countable. Now, most of the time, if we want to compute future probabilities, we need to know the initial distribution of the process. The initial distribution of the process is just the distribution of the initial of x0. Okay. And since it's a discrete random variable, takes values in a finite set S, then, or let us say S from 0 to L, then the distribution is just actually given by a probability vector. Okay, so we have to know P of x0 equals 0, P of x0 equal 1, and P of x0 equal L. So we have the distribution is given by a probability vector. And since it's a distribution, each entry is non-negative and the sum is 1. Okay. When xn equal I, we say that the system is in state I at time n. Okay, and we shall learn how to compute such probabilities. Okay, given the transition matrix and the initial distribution, we'll learn how to compute the probability that xn equal I, or that the system is in state I at time n. Okay. Now let us give some examples. The simplest example is just a two-state system, okay, that can model actually a phone which has two states, busy or available, and available. The first state, so busy, will be denoted by 0, and available will be denoted by 1. Okay, this is just convention. And we are interested in the states of this phone at each minute, let us say. So time is discrete here. Okay. At each time step, the phone is either busy or available. Okay. So this is a Markov chain, but in order to give a complete description, we need the transition probabilities. So we have to say them explicitly. Okay, this is the assumption. If the system is busy, if the phone is busy, then there is a probability of 40% to stay busy, and therefore a probability of 60% to be available. Okay, this is the given. There is a redundancy here because it's enough to give one of them. And now if the system is available, then there is a 30% to chances to stay available, and of course a probability of 70% to move to the busy state. Okay, so these are the assumptions of the simple phone system. So if xn denotes the states of the system at time n, then we have a homogeneous Markov chain whose transition matrix is given by 04, 06, 07, 03. This transition matrix is actually what we call a stochastic matrix, because each entry is non-negative and each row sums to 1. Okay. So one way of specifying Markov chains is to give the transition matrix, and another way is to analyze them sometimes is by giving the transition graph. The transition graph of a matrix chain is what we call a directed graph, if you studied or are studying now graph theory. So it's a directed graph. Here we have two vertices, actually 0 and 1, and we have arcs, oriented arcs, actually connecting the states. Now, of course, you can put the arrow in the middle. It's not really important. You can put the loop here. Okay, but this is how the transition graph looks like of a homogeneous Markov chain. Okay, so here we are just saying that if we are at state 0, we will remain there with probability 40%, and we can move to the next state with probability 0.6 and so on. Okay. Next example, a simple bonus-malus system. The bonus-malus system is usually used by automobile insurance companies that classify their policyholders into categories. Now, in this simple model, there are just two categories, low risk and high risk. Usually, if you are in the low risk category, the premium, you will have to pay a smaller premium, right? And if you are high risk, then you have to pay a higher premium. Now, so we have two states here, actually. We can move between them. But the company in this simple model will estimate the transition probabilities as follows. So based on statistics of previous years, the company found that if the client is low risk, there's 35% chances to stay low risk. And therefore, there is 65% chances to move to the high risk state. And if the client is already high risk, then he will stay high risk with probability or with 55% chances. And therefore, 45% he will move to low risk. And therefore, here time is measured in years, so it's discrete. And if xn denote the state of the client, so we denote the low risk state by 0, the high risk by 1. So if xn denotes the states, so xn takes just two values, 0 and 1. And so we have then a Markov chain, a homogeneous Markov chain with this transition probability. And the transition graph looks the same as the previous example. Okay. Next example, also two-state model. Simple weather forecasting model. In this model, we suppose that if it's raining today, there will be a certain probability. It will rain tomorrow with a certain probability, and it will not rain with the opposite or the complement probability. Okay, so if it's raining today, it will rain tomorrow with probability P, and if it's not raining, today, it will rain tomorrow with probability Q. And therefore, if we denote the rainy state by 0, and the non-rainy state by 1, just a very simple forecasting weather forecasting model, just 2 states, rainy or not rainy. So we have the state of the system. So time here is measured by days, okay? And if xn denotes the state of the weather at day n, then we have a homogeneous Markov chain whose transition probability matrix is given by P1 minus P, Q1 minus Q. Okay, so it's just enough to give 2 numbers because the other 2 are related. Okay, and of course here we can draw a similar transition graph. Okay, in the exercises we shall see a little bit more complicated forecasting model with 3 states. Okay. Next example, a random walk with absorbing boundaries or the gambler's ruin model. Okay, so we have the same model for 2 situations. I will explain them both. Okay, so consider a drunk person who walks along positions 0, 1, 2, 3, 4. So we have 5 positions, 5 states. And you can move to the right or to the left with probability to the right with probability P and to the left with probability 1 minus P. Okay, and since the state is finite, when we reach probability 0, okay, when we have absorbing boundaries, if we reach state 0, we stay there forever. Okay, and same thing if we reach state 4. So this is why they are called absorbing boundaries. So the game ends actually in this case. Or if you like, if time will continue, then the system will stay in the same position forever. So if xn equals 0 at a certain time, then xn plus 1 will be 0 at the next time. Okay, so if xn denotes the states of the walker at time n, then we have a homogeneous Markov chain on this 5-state space. So the probability of moving from 0 to 0 is 1, is certain here, and so we cannot move from 0 to 1 or to 2 or to 3 or to 4. If you are in state 1, we can move to state 0 with probability 1 minus P and with probability P to state 2 with probability P, but we cannot move to others. And same thing for state 2, 3, and 4. Okay, so this is the transition, the probability transition matrix of this chain. And the transition graph looks like this. So we have 5 states. If you are at 0, we remain there. If you are at 1, we can move either left or right. And same thing for 2, same thing for 3. And if you are in 4, you stay there forever. So this is what we call the random walk, or a random walk with absorbing boundaries. Okay. Now it's possible to have Markov chains where we have loops here. So the diagonal entries are not 0. But usually they are not called random walks. Okay, maybe they can call generalized random walks, but what we usually call random walk is we are not allowed to stay at the same position unless we are at the extreme ends. Okay. Now in the next chapter we'll consider a random walk on Z. So the state space is infinite. Okay. Now why it's also called the gambler's ruin model? Because this situation models a gambler playing a game, and at each step he wins $1 with probability P and loses $1 with probability 1 minus P. And the game ends when either the gambler is ruined, so he has a total fortune of 0, or he achieves, for example, here in this case, 4, a total fortune of $4. In this case, he leaves the game. Okay, so this is called the gambler's ruin model. Now, we are not obliged to work on 0, 1, 2, 3, 4. We can work on any finite set. So more generally, a random walk with absorbing boundaries on this state space 0, 1 through L is a Markov chain with transition probabilities. So this is what I was saying. So we can move from to the right with probability P, or we can win $1 with probability P. We move to the left or lose $1 with probability 1 minus P. And when we go bankrupt, we leave the game. So, and when we achieve a total fortune of L dollars will also quit the game. So, so random walk with absorbing boundary or gambler's ruin problem are actually have the same Markov chain model, which is a matrix that looks like this actually, but its length can be arbitrary, its size can be arbitrary. And yeah. Now, next example, random walk with reflecting boundaries. So same problem, a walker or a gambler. So if we are in the case of a walker, we can move to the right with probability P and to the left with probability 1 minus P. If we are in the case of a gambler, we win $1 with probability P and lose $1 with probability 1 minus P. But now the boundary conditions are a little bit different. So this is L, not M. So we have, the situation is like this now. When we reach a total fortune of 0, some good man gives $1 to the gambler, and so he can continue the game. And if he reaches the state L, so if his total fortune is L, then in the next state, he gives $1 and moves to state L minus 1. Okay, so now the boundary conditions are a little bit different. So we have the same model for two problems: a random walker with reflecting boundaries, or a gambler's with a special game. Okay, so in this case, the game will continue forever. Okay, right? So it will never stop, theoretically. Okay. Next example, a little bit more interesting, a more complex bonus-malus system. Now, instead of just classifying the policyholders into two states, high risk and low risk, the insurance company classifies them into 4 states, according to from low to high. So 0 is low, then higher, then higher, then higher. So it just have 4 states. And the policyholder state, so we move from state to state. So time is measured in years here, in response to the number of claims made by that policyholder. So a claim is actually, what is a claim? A claim is when the policyholder has an accident and goes to the company saying, I made an accident, please pay me. Now, usually a claim is equivalent to an accident, but not necessarily, because the client can make an accident and not go to the company. Okay, so it's not considered as a claim in this case. But usually we model claims and accidents by the same random variable, which is a Poisson, as we shall see now. Okay, so here again we have a Markov chain. An object or the state of the client varies from year to year between the states 0, 1, 2, and 3. Usually, when you are at low risk, the premium is lower. Okay, this is the idea behind classifying low risk and high risk clients. So the higher risk you are, the bigger will be the premium that you have to pay to the insurance company, because you are a risky person. So you are likely to make more accidents, and therefore the company, you have to pay more to the company. Okay, so in this hypothetical example, this is the policy of the company. So we have 4 states. So low risk, the lowest risk, you pay $200 per year. If you are at state 1, a little bit higher risk, so you pay a bigger amount, $250. If you are still at a higher risk, you pay $400, and if you are at the highest risk, in this simple example, you pay $600 per year. Now, how can we, in this model, can we move from state to state? Okay, if you are originally at state 0 and make no claim or make no accidents, let us say, then we remain at this low risk state. If we make one claim or one accident, okay, so we are more risky now, we move to the next state, 1. So we have to pay a bigger premium. If you make 2 claims, then you move to state 2, and then you have to pay $400. If you make at least 3 claims, then you move to the highest risk, 3, and then you will have to, next year, you will have to pay $600. Okay? So from state 0, we can remain at state 0, we can move to state 1, 2, or 3. Now, if we are in state 1 and make no claim in the year, then next year we'll go back to state 0 and pay less. However, if we make 1 claim or 1 accident, then we'll move to the higher risk state and pay $400, and so on. I think if you are in the highest risk and make no claim, then you will be decreased and pay less next year. However, if you do 1 claim or more, then you will stay as state 3. So from state 0, we can go to 0, 1, 2, 3. From state 1, we can go to state 0, 2, and 3, but not to we cannot remain in state 1. If you are in state 2, we can move to 1. We cannot remain in 2, but we can move to 3. And if you are in 3, we can move to 2 or remain in 3. Okay. Now, so this is a Markov chain, but the transition probabilities are not given so far. Okay. Of course, we can draw the transition graph if you like before we compute the probability. So let me. Okay. So this is the transition graph. From state 0, we can remain at state 0 or move to 1 or move to 2 or move to 3. From 1, we can move back to 0, we can move to 2, and we can move to 3. If we are in 2, we can just move to 1 or to 3. And if we are at 3, we can go back to 2 or state at 3. So this is the transition graph of the Markov chain. But it's incomplete because now we have to compute transition probabilities. Okay. In order to do that, we have to model the number of claims as a random variable. And this is usually done by using a Poisson random variable as a certain parameter that the company estimates using statistics. Okay, now why the number of claims or accident is modeled by a Poisson random variable? Because really it's actually a binomial random variable with a big number n and a small probability p. So suppose that you have 1 million cars, and the probability that each car makes an accident is very small, like say 0.1%. So the product is small. So lambda in this case will be 1,000. Okay, so we already saw that actually in the chapter 0. So here, the Poisson random variable is used as an approximation of the binomial random variables. The binomial random variable needs 2 parameters, n and p, and the Poisson random variable just needs 1 parameter, which is lambda. Okay, and the distribution of the Poisson random variable is, as you know, given by this formula. Okay, so the probability that we have k claims is lambda k over k factorial times e to the lambda. Okay. Now, having assumed that, we can compute the transition probabilities between the 4 states. Okay, now this is interesting actually. Okay, how do I know that the transition probability matrix is given by this way? Okay, so you can write here state 0, state 1, state 2, state 3, and same thing, 0, 1, 2, 3. Okay, what is the probability of moving from 0 to 0 or just remaining at 0? Okay, let us look at the table here. In order to stay at state 0, we have to make 0 claims. What is the probability of making 0 claims? It's just lambda 0 over 0 factorial e minus lambda. So it's e minus lambda. So the probability of remaining at state 0 is e minus lambda. What is the probability of moving from state 0 to state 1? This happens if and only if we have 1 claim. The probability of 1 claim is lambda to the 1 over 1 factorial e minus lambda. So it's just lambda e minus lambda. What is the probability of moving from state 0 to state 2? We have to do 2 claims exactly. The probability of doing 2 claims exactly is lambda 2 over 2 factorial e minus lambda. And now, what is the probability of moving from state 0 to state 3? To do that, we have to do at least 3 claims. So there are 2 ways of computing that. It's the probability of making 3 claims, or 4, or 5, or etc. So we can write this as an infinite series, sigma from k from 3 to infinity of lambda k over k factorial e minus lambda. But we can write this infinite series as 1 minus the previous probabilities, because the probability of making at least 3 claims is 1 minus the probability of making 0 claim, 1 claim, and 2 claim, as you know from the properties of the Poisson random variable. So the computation of the fourth entry here is not difficult. And we already, of course, we know because it's a stochastic matrix, so the first entry should be 1 minus the sum of the first 3. Okay, so you have 3 ways of computing this probability, actually. You can write it in 2 ways, as an infinite sum, as an infinite series, or as a finite series. And if you continue in this way, okay, what is the probability of, if you are at state 1, what is the probability of moving to state 0? Is this equal to the probability of making 0 claims? So it's e minus lambda. Now, from state 1, we cannot move to state 1 according to this table, but we can move to state 2. If we move to state 2, if and only if we make 1 claim. So, and the probability of that is lambda e minus lambda. And the probability of moving to state 3 is to make at least 2 claims. And this is given as before as 1 minus the previous 2. Okay. Now, if we are in state 2, we cannot move to 0, but we can move to 1 if we have 0 claims, so with probability a minus lambda. We cannot stay at state 2, but we can move to 3 with probability 1 minus e minus lambda, because now it's clear. And finally, if we are at state 3, we move either to 2 or to 3. We move to state 2 if we have 0 claims, so this happens with probability e minus lambda. And the complementary probability is just 1 minus that. So this is now the transition matrix of our Markov chains, and lambda is a parameter usually estimated by the company using statistics of previous years. Okay, so we already saw the transition matrix. How does it look like? Of course, in practice, there may be more than 4 states. In the literature, the book of Rolski gives an example with 18 states. Okay? But usually to analyze this, we cannot do that on paper and pen. We have to use computers, actually. And to finish the example, if you go back to the snake ladder game, we have 100 states, and therefore the transition matrix is 100 times 100. So once again, we cannot analyze it using a paper and a pen. However, we can do it. We can do simulations using a computer. And I will give you later a project to estimate the time till the end of the games. Okay, we should go back to this later. Okay, so I think this is enough for this video. In the next video, I will continue the remainder of section 1.1. So thank you for your attention and see you later.